Hello everyone, this is Mohammed and welcome to another video tutorial on model predictive control and in its implementation using Casadi. Um, just a quick note, if you haven't seen at least the first video lecture in this playlist, so please do so before watching this video, or otherwise this video will be completely a nonsense to you. So I have received many questions from those who have seen already the first two lectures um, about the implementation of MPC for a trajectory tracking problem and how to do this in Casadi. So in this video tutorial, I'm going to show you how to do this, which turns out to be a very straightforward extension to the code we already discussed before for the point stabilization control problem. Um, so again, I'm going to use the mobile robot example as an implementation example. So let's go ahead and first recover or recall the dynamics model of the system we are considering, which is basically a differential drive robot system that has this kinematics model with three states, x, y, and theta. Um, x and y are the position states, and theta is the orientation or the heading of the robot, the heading angle, I mean. Um, Remember that we talked about two common control objectives in control problems in general. The first one being the point stabilization problem, where the reference we would like to stabilize our system to is a fixed point in time. So for example, if we're looking at a point stabilization problem for this mobile robot, um, we set the reference to be these three values for the x position, the y position, and the angular position theta. And these three values are fixed for all the time steps. On the other hand, if we have a trajectory tracking problem, this means that we have, or we would like our robot to follow a certain trajectory that has different states, or that has states that evolve with time. So let's recap the model predictive control, or the MPC formulation for a differential drive robot. So we said that we will use an Euler discretization of the kinematics model, and we will use this discrete time model to predict the state of the robot, right? And then we said, well, our MPC controller running costs is going to be a penalization for the deviation between the predicted state of the robot and the reference state, and also the penalization for the deviation or the difference between the control action we would like to apply and the reference control action. Then we formulated our optimal control problem, or OCP, for our MPC controller, where we would like to minimize a cost function that is simply a summation over a certain prediction horizon length n for the running costs L that we showed up here. Then we would like to minimize this cost function while the minimization is subject to these constraints. Of course, one of the most important constraints is basically the dynamics model. Actually, this formulation in this form is valid for both point stabilization problem and the trajectory tracking problem. And like, as this boils down to the way we define the xref and uref. Like if xref and uref are fixed with time, so that's the point stabilization. If xref and uref are changing with time, then it's a tracking problem. So let's recap what we did in the point stabilization problem. So in a point stabilization problem, our robot starts from an initial condition x0, and we would like to stabilize it to a reference position and orientation, as you see here. So let's say that this reference position has the state 2, 2, and 0, like we would like our robot to move 2 meters in x, 2 meters in y, and stabilize its orientation to 0 degrees or 0 radians. So this vector is actually our xref vector. All right, so what about uref? So uref is the control action that would stabilize the system there. So if we'd like our robot to be there, we simply set its speed to zeros, right? So let's look now at our optimal control problem we saw in the previous slide, and let's expand the objective function, or Jn, for a prediction horizon length n of 3. So let's say that n equals to 3 and expand this Jn. So if we do so and substitute with the values for xref, since this is a point stabilization problem, you will see that the three terms for the running costs has basically a fixed xref. So for like 2 to 0 here, and that's repeated for all the time steps or all the prediction steps, and also uref is fixed and equals to 0 for all the prediction steps. So now let's look at the trajectory tracking problem. So here's our robot again, and this time we would like our robot to um, like track a trajectory instead of just being stabilized at a particular point. So for simplicity, uh, let's take a trajectory that is parallel to the x-axis with this equation. So the x position, or the reference x position that we would like to track, is it changing with time, and the with a constant y position and a constant orientation. So this reference means that we would like our robot to go from left to right along this line while the robot is facing the positive x direction. So the first thing you would note here about this reference, that this reference now is a function of time. So the reference is not fixed anymore as the point stabilization case. So for example, when the time t here is 0, xref becomes 0, 1, 0, and that's the first point along my trajectory. And when t equals to 24, for example, the reference vector becomes 12, 1, and 2. And let's take this as the endpoint of our trajectory. So this is xref so far. So what about uref? So we said that uref is the reference control action that would make my robot go along this trajectory. Alright, so how to get this? Actually, we should have a look at our kinematics equation in order to be able to get uref. So we know that uref has two components, v and omega. So looking at the kinematics equation, if we square and add the first two equations, we will end up having this equation, x dot square plus y dot square equals to v square, because if you square this term and add it to the square of this term, you will have sine square plus cosine square, and this is basically 1 multiplied by v square. So now, having this formula, if we find the first derivative of the x position, or the reference x position, and the first derivative of the reference position in y, we will end up having that v equals to 0.5, because if we go up here, so this is x of t, so its derivative is 0.5, and this is y of t, and its derivative is basically 0. So this equation boils down to v square equals to x dot square, or v equals to 0.5 meters per second. Now, by looking at the third equation here, we simply have omega equals to theta dot, or the derivative of the orientation. So going up to our reference xref, and then going to the reference for the orientation, which is 0, and this means that its derivative is also 0, and this means that the reference for omega, or the angular speed, is 0 radians per second. Actually, these two control actions, or these two values, form my uref, or the reference control actions. So we have a 0.5 meters per second reference control for v, and the 0 radians per second reference control for the angular speed. Actually, this uref is also called the feed forward control action. So these are the control actions that if my robot is starting from the right position at the right time on this trajectory, and then we apply these control actions or feed forward control actions, the robot would follow exactly this trajectory. So now that we know our xref and uref of the trajectory we would like to follow or track, so let's expand the objective function of our optimal control problem for n equals to 3, similar to what we did in the point stabilization case. So in order to do so, we have to get the first three reference points along this trajectory. So let's say, for t equals to 0, the first reference along this trajectory becomes 0, 1, and 0. And then let's say that our sampling time is 0.5 seconds. So this means that the next reference point along this trajectory is obtained by substituting t equals to 0.5. So if we go to xref and substitute t equals to 0.5, we end up having this reference posture. And then the following time step for t equals to 1, this becomes our reference for the state vector. For the three cases, and actually for all the points along this trajectory, uref is constant. It's 0.5 for v and 0 for omega. So let's now expand jn. So as you can see here, jn is expanded for n equals to 3. This means that we are adding up 3 running costs. So as you can see, xref is changing for every time step, and uref is constant here, but it's not 0 anymore, as in the point stabilization case. I just would like to um, let you know that this is a very simple trajectory tracking problem, or it's a very simple trajectory to follow. But in other cases, we can have t appears everywhere in xref and uref. So I'll show you how to program an MPC controller for trajectory tracking problem for this xref and uref, and this is or can be generalized for any type of reference trajectories too. So let's look at the Matlab implementation for the trajectory tracking problem. It turns out that we will use mostly the code we used for the point stabilization case, and we will have just a few changes to implement the trajectory tracking. The first change is with the definition of the vector p, where we previously had this vector of size n states plus n states. So the first n states elements in this vector were my initial condition, and the other elements were my reference state or xref. In the trajectory tracking case, we again have the first n states element, but we have more elements to define the reference trajectory. So what we have extra this time is that we have the number of states and number of controls times n parameters. These parameters are my xref and my uref for all the prediction horizon steps n. So now moving forward with the Matlab implementation, we will stop again at the definition of the objective function or the variable option. So previously in the point stabilization case, we had the penalization of the deviation between the predicted state and the reference state. And as you notice, or as you can notice here, the reference state, which was a specific portion of P, was the same for all the prediction steps. But for the trajectory tracking case, which we are considering in this video, we are like for every step along the prediction, we are penalizing the deviation between the state and a different reference, because for each step along the prediction the reference is changing. And the same with the control. So what we have from P here is the reference state, and what we have from the parameters vector or P here is the reference control. So in the point stabilization case, as you can also notice, we were directly penalizing the control action because the reference at that time was just 0. So we simply penalize the control action directly, and this means that we are penalizing the deviation between the control action and simply 0. So now moving forward with the implementation, everything remains the same as the point stabilization case until we stop again at the simulation loop, where we fill the variable args.p by the initial condition and the reference for all the controls and for all the states. Alright, so previously in the point stabilization case, we were filling this vector by just the initial condition and the reference condition, which was fixed. But now, as the reference is changing for every prediction step, we will fill the args.p vector differently. So again, the first three elements in the args.p are going to be the initial condition for the robot. And inside this for loop, we will fill the rest of args.p. Here we are filling args.p by the reference state, xref, yref, thetaref. And here in this line, we fill args.p by the reference for the control actions, which are the uref, which is vref, and omega ref. Right? Okay. So I'm defining a new variable inside this loop, which is called the current time, and this current time gives us or tells us the time that corresponds to the current MPC iteration, and it basically equals to MPC iteration times the sampling time t, right? So going back again to this for loop where we define our reference, we calculate the time that corresponds to the predicted step, right? And this predicted time is basically my current time plus the predicted step times the sampling time, right? So knowing this t predict, we can now calculate xref, because xref is function of time, right? Yref and thetaref remains the same because we are considering that straight line reference trajectory. We also define uref and omega ref, which are my reference for the linear speed and the reference for the angular speed of the robot, right? And we derive these two values in the slides. This if condition is simply a stopping condition that marks the end of the trajectory. So we say that if xref, that keeps updating up here, if this reaches the value of 12, then our robot should stop at this position. So let's run the code now. So I'll go to editor and then run. So we'll get this closed loop performance. So as you can see, this is our reference trajectory, and you can see that the robot converged to that trajectory and kept tracking it. And as the robot reaches the end of the trajectory, the reference becomes the same point and the robot stops there. So when the simulation ends, you will see a graph for the closed loop control actions for V and omega. So if we have a closer look at our control actions, so you will see that during the transient part where my robot was like converging to the trajectory, the control action was just hitting the limit of the maximum speed, which is 0.6 in this case, and then it converged down to 0.5, which is the reference control action that we set, right? And as the robot reaches the endpoint of the trajectory, the reference for the linear speed becomes 0 again, because now our problem, or the problem, is a trajectory tracking, sorry, a point stabilization problem at the end, right? And for the control action omega, so initially the control action was changing as the robot was, turning left here, and then overshoot a little bit, and then turn right to converge to the trajectory, and then this value kept to its reference value 0, which was the case for the tracking case and the point stabilization case. So that's it pretty much for trajectory tracking. It turns out that it's very similar to point stabilization, except for the few changes we saw in this video. Thank you very much for watching.